that the LHC now functions very well and has started up and even made some events and has been running well little before Christmas and will start again in the middle of February.
Uh-huh. All right.
And then to do really serious running.
So this is obviously what everyone is waiting for. And, as I mentioned here, we definitely want to examine this more in detail, some of your theories and so forth. Maybe you just can give us a little bit of background first here for our listeners about Niels Bohr and the work that you guys do down at the Niels Bohr Institute, if you will.
Oh, at the Niels Bohr Institute, we have groups working at some of the experiments being done at the LHC. That's not me, that's the experimentalists. We have experimentalists who really do the experiment, and they work at the intersections of the beam. This big accelerator there is a 27-kilometer ring where the particles run around, some the one way and some the other way. And this is protons, or it can be heavy ions. And then at some intersection places, they are organized to the beam going the one way and the beam going the other way are organized to collide. Mm-hmm. And this around these places where it is organized, one has built up some big instruments to measure what comes out when the particles collide, and perhaps interesting particles will come out, such as the Higgs particle we are looking for, and perhaps other particles.
Absolutely, and maybe you can mention to us a little bit about the Higgs boson, or in some circles it's known as the God particle. What is this?
Yeah, one calls it the God particle, yeah. But the Higgs particle is really a particle in the so-called standard model, which is the best model so far. And in this model, there is a funny feature that if you didn't have this Higgs particle, then all the other particles in the standard model, the best model for the present time, would be massless. So they, in the sense that they would have no rest mass, which really means that they would move all the time with the speed of light, 3 times 10 to the 8 meters per second. So they would always move this way if it was not for the Higgs particle. So the Higgs particle is a needed extra thing in the model in order to give them the masses which we actually have measured, so they are known. And therefore the Higgs particle is known in order that the physics should be like it seems to be. Or else something else than the Higgs particle has to take over the job of the Higgs particle and do this job instead.
What is your point of view in terms of the standard model then? Do you guys have another theory, or do you go along with the standard model?
Oh, there are many theories on the market, especially, for instance, superstring theory versions. And they are usually some extension of the standard model. So for instance, if you have the superstring type of theory, then you will typically expect that you have, in a sense, rather 5 Higgses than 1 Higgs. You have more Higgs particles predicted to come. But so you don't really have the Higgs, but you have several Higgses, and one of them more or less looks like the Higgs. So it's very close in that sense. But there's also a type of model called technicolor models, in which you make, roughly speaking, the Higgs particle be replaced by a bound state of some, then in this technicolor model, existing particles. And these bound states can then explain more naturally that this Higgs particle, or Higgs, in this case, Higgs particle replacement, has a surprisingly small mass, or has a mass that is small, in spite of the fact that it is very difficult in the technical calculation to keep the Higgs mass small, because you tend, when you calculate corrections to the Higgs mass, to get big contributions, and then it is big compared to what the mass is. So you expect, it's very surprising that the Higgs particle is so light, because it's even difficult to keep it light as you go along in the calculation.
So to me, when I'm listening to this, it almost sounds to me that something is obviously, there's a big puzzle piece here missing in order for our understanding of the universe to come together. So something is missing, and we're still looking for the evidence which is going to confirm our model of the universe. Now, do you think that we could be totally wrong? Could there be something else going on here,
No,
Holger?
I think it is a very natural thought that this standard model is not the final model. There are actually several reasons for that. And I think most people, most physicists, expect that the standard model will show wrong already at the LHC.
Yeah.
I am probably a bit special by expecting that the standard model will turn out right over the LHC, so that LHC will confirm the standard model, and the standard model first will turn out wrong at much, much higher energies, which are so expensive to build accelerators for that we don't even care to send in applications.
So tell us a bit about some of the claims that you've made and so forth as well. That there's something that seems to be going on in terms of the efficiency, shall we say, of the Large Hadron Collider. It's not working properly. It's been stopped so many times now. What do you think is going on here?
Yeah, that's right. I mean, one can say that at least there was an accident last year. In 2008, in September, just when it was about to start, and one had the next month the inauguration of the machine. Then it occurred an explosion, an incident that made it stop for more than a year.
Yes.
And this was, of course, a sign of bad luck. And there was another machine, the SSC, in Chicago. No, not in Chicago. In Texas, which was should have been bigger than the LHC, in the sense that the beam of the SSC should have had 20 TeV energy per particle going around the ring, while in LHC it is 7 TeV, and this TeV stands for tera electron volt. And this is an electron volt is the energy an elementary charge gets by going through a potential of 1 volt. And tera means 10 to the 12, so it means million. So a million. So in the LHC, when it comes to its big running, would be 7 TeV on 1 proton and 7 TeV, which means 7 million electron volt energy on 1 proton going against another proton with the same energy of 7 TeV, so that together they will have 14 TeV.
Yeah.
And there will be in the center of mass, in the collision, 14 TeV energy available in principle for producing new and interesting particles. It is difficult to get it used all in an effective manner, but there should be good chance for producing a Higgs particle, which, for instance, could have, as I believe myself, 115 GeV.
So a tremendous amounts of energy here, obviously, that is being used in order to clash these particles together to kind of. I mean, I've heard in some circles that this could potentially, open a portal in terms of dimensions and things like this. That it could in some way upset the normal physics here on Earth, for instance. Have you heard about this? What's your theories about this?
Oh yes. Now there is in the superstring theory type of ideas, there is a proposal. Or there is the idea going that there should be extra dimensions.
Yes.
So one of the possibilities for interesting things to happen at LHC is that one could discover that instead of the usual number of dimensions of 3, we have, so to speak, 3 coordinates needed to fix the position of a point, up, down, east, west, or north, south. And instead of the 3, then in superstring theory, there is in principle 9 space dimensions and 1 time dimension. And therefore, there could very well be some extra ones. And then these models might make it possible to somehow see particles that signals that there are these extra dimensions. That would be called Kaluza-Klein particles. And there's also on the market some story that one could use this to make the mass parameter in gravity combined, gravitational constant combined with other parameters. That gives you can construct a mass which would be somehow the most fundamental mass and cause the Planck mass. And this Planck mass unit, which is somehow suggestively the best unit you could have of if you should guess what is the natural mass unit in physics, that is a mass unit that is 10 to the 19 GeV. This is a mass of some sort of little salt corn or so. So it is a millionth of a gram or so. It's on a human scale a small mass.
Yeah.
But compared to the masses of the particles you can see at LHC, it's enormous.
Yeah.
Far too big. If you had a particle with that mass, you couldn't dream about producing it at LHC. Far too big. And the mass of the Higgs particle, which we expect it to have, we know the order of magnitude of it, so the order of magnitude we know would be about 10 to the 17, enormously much smaller than this Planck mass. And that is actually one of the very interesting problems. Why is the Higgs mass so small compared to the presumably fundamental mass?
Yeah. Any answers to that? Any theories about that?
Well, this is a scale problem, and well, I would of course claim that I have a model where we have a sort of answer to this, but that is that probably nobody will believe in. But in superstring theory, and there is an attempt to not completely solve that, but to partly solve that problem by trying to do that at least when I make corrections to this little Higgs mass, then I don't get it big immediately, but I just shuffle it a little bit and not a big bit. You see, if I get, even if I assumed that a fundamental parameter in the theory related to the Higgs mass was very small, then it turns that when you correct it a little bit and calculate what you should really see as the Higgs mass and the thing that you really know is small, then it would deviate a lot. So you would have to say that the parameter giving the Higgs mass should be adjusted not to be small, but to be big at a place where it would just, when being corrected, would be small. It sounds even more crazy that way, you see?
It does in one way.
And this last problem of shuffling it around by big quantities, this can be solved in the series which have the so-called supersymmetry, which means in the series of the type of the superstring theory. This is this aspect that gives the name super to the string theory, which is important for solving that problem.
I see. And you tell us a little bit about your model then, the model that you're developing.
I have a model. Of course, as you mentioned kindly, I am also a father, one of the fathers, although in some sense a bad one, for the superstring theory or the string theory.
Yes.
But I have a model which was the one you mentioned, came in New York Times, and this is a model which we announce as being the suggestion that the action is a complex quantity instead of a real quantity.
What does that mean?
Yeah, that's right. That would mean that I should explain what an action is. And an action is a quantity that is a function of a history of a system or of the whole world, if you wish. So you put in a history, and then, according to some formula, you calculate a number. And this is what one could call a functional. And this is a type of functional of a history that could be, for instance, the action. And this action is used very often by physicists to tell to their colleagues when they have a certain model or a certain theory. Because instead of writing down all the equations for how the forces and the accelerations and so on are in their theory, how the particles move around and what equations the fields obey and so on. Instead of doing that, they can write an action which is then a formal expression for how you calculate from a history this quantity, the action. And then by manipulating this action in a certain mathematical way, you can get all these equations which are in the theory. So it's a way of a shorthand way of telling your colleague what is your theory. And this action is very practical in that sense, and it was invented in the, I think, 1800 numbers. It goes back to the what is now the next to foregoing century. I see.
And so what does your theories about the future say here as well?
Yeah,
then?
Now we have, now this action, I could also mention, is coming into a formulation of the quantum theory which one has to use today, which was developed by these people, Bohr and Einstein and
Heisenberg.
Heisenberg and was initiated by Planck.
Yes.
This quantum mechanics can be formulated according to a functional integral, what says, but by means of an action. Where by means of formula where one involves the action. And then basically our theory consists in that instead of, as one usually does, and what is probably the truth, that this action is a real number, is just a positive or negative number with many decimals, of course, for each history, then we allow it to be a complex number. So we say we have, in addition to the real part, we have I times another real number. And this I is a square root of minus 1. You know that complex numbers, they are obtained by essentially pretending that you can find a square root of minus 1 or of negative numbers.
Mm-hmm.
You know that in true real number working, square root of negative numbers is nonsense. There are no negative number multiplied by itself that gives a negative number.
Yeah.
But there is in the complex numbers, and then you denote these ones by means of the I. The I is a minus square root of minus 1. And in the complex number system, you can take square roots of negative numbers also, of all numbers.
Mm-hmm. Mm-hmm.
And then that is the game. But that is somehow all the mathematical things. Then we calculate in principle with this Feynman-Wenzel-Dirac functional integral, this method of getting quantum mechanics by means of the action. And then we have not calculated exactly, but we make a lot of speculations and so on. And then we come to the approximation that very likely we may still get essentially the same equations of motion approximately as you got in the theory without the imaginary action, but that this complex action but that the part of this action, which is a new part, the one that multiplies the I, which is the square root of minus 1, that will get the role of being an expression that will determine which solution to the equations of motion is going to be realized. That is to say, these equations of motion we have in the coming out when we use the real action, these equations of motion, they have many solutions. You can think of Newton's second law that you have the acceleration is equal to mass times acceleration is equal to force, and then you can solve and find many solutions to this. For instance, you can have the famous apple falling, but if you, instead of letting it fall, throw it a little bit up, it falls in a different way, but it is still a solution to the equations of motion.
Right.
So you have many possible developments that agree with the equation of motion. And that could also, you can think of the whole world as developing according to some equation of motion. And then I'm stressing that there are many possible ways it could start, and they will give different developments. But depending on the start, you get different developments. So now we are so ambitious that we would like also to determine the start and get that out of our mathematical formalism. And then the point is that this extra part in the action, which is the imaginary part, the one that comes to the little I, which is the square root of minus 1, that part is supposedly determining not so much the equation of motion, but rather the selection of the solution to the equation of motion, which means how the system started. So what I am saying in short is that the universe, or your system, gets started in such a way that a certain quantity, which is called the imaginary part of the action, should be actually as small as possible, as negative as possible. It's probably negative, so it should be numerically big but negative. And this then selects just that right start, which the universe takes.
So what you're talking about is basically how it all began. We're talking a big bang here.
That's exactly right. Yes.
Yeah.
I'm saying that how it began is to be determined in our model by the beginning that would give the most negative value for the quantity called the imaginary part of the action. And the imaginary part of the action is that part of the action which stands in the complex action with a little I, which is the square root of -1 in front.
Huh. So how is your work being done? Or are you guys sitting around and calculating a lot? Do you run computer models, or how do you go about tackling it?
In principle, you could now think of a kind of God in quotation mark, evaluating for every solution to the equation of motion, which means everything agreeing with Newton's second law and so on, the equations for the field, the usual equations of motion from the real theory. He would calculate what is for this start, and for this start, another start. He would calculate this imaginary part of the action. According to a moderately simple formula, you can write it on a few transparencies. But to calculate it for all histories of the universe, that's of course beyond any computer realistic.
Yes.
But for God, in quotation mark, maybe everything is possible. So he would do that, and then he would select precisely that start, that history, you could say, which is given by the start, which would give the minimal value, which means the most negative value of this imaginary part of action.
See, if we even further try to clarify this, would you say that we are talking about that this model would kind of suggest that there is a God here in the picture, that there is a force here who is guiding events, or what's the outcome of this? What's your
you can say that when I talk about God in quotation mark, it really, of course, just means that this is a way of talking about our model, and this is not really God or so. Okay. But I think that this having a mechanism to determine the initial conditions, the starting conditions, in the way I have been describing, that is extremely close to a God in a way.
Yes.
Because it is like having a government of the development of the universe. Because this imaginary part of the action, it does not really only depend on what goes on in the beginning, but in principle it depends on what goes on at all times of the history you put in.
And the history we put in is that in terms of this creation cycle, from the terms of the Big Bang and forward, and into the future,
right.
the future as well.
You put in the history from Big Bang, if there was a Big Bang, maybe there wasn't really a Big Bang, but whatever. Yeah. From the very beginning, whatever it was, whether there was anything before Big Bang or there was not, you put in from the start to the end, say. And then you calculate this action, which is a function of a history, I said. So you evaluate it as a certain integral mathematically, which involves what this history tells about what happens at all possible times, even including the future. So it means that this action, and that means especially the imaginary part of the action, which is part of action, just this action depends on what goes on at all times. It doesn't have to depend equally strongly on what goes on at all times. And if our model should not be completely out of question experimentally, we must find an explanation that it depends mainly on what goes on in Big Bang time or close to Big Bang or something like that.
Yes.
Because that is what it seems experimentally. But in principle, it depends on what goes on at all times. And therefore, in principle, it is like a government of the whole development of the universe. And this is really smelling very much like a god.
Yeah, exactly.
Because this is God's job somehow. He is the leader of the universe, and he is leading it with taking some care of all times.
Yes.
Maybe mainly care of the beginning, but in all times.
So also what
and
this...
therefore, in principle, this minimizing this imaginary part of the action could lead to various miracles occurring if there could be some miracles which could contribute to make this imaginary part of action especially negative.
So in one way here, what is happening here now as well with the Large Hadron Collider is that they're trying to recreate basically this moment from where this God in quotations then comes into the picture and sets things in order, so to speak. And what they're doing here at the LHC is they're trying to replicate this Big Bang moment, if you will.
Yeah, that is right. That you can describe that these accelerators to some extent replicates the Big Bang situation because they collide the particles with high energy, and in the Big Bang time, the particles there was very hot.
Yes.
And the particles were running with big energy. So in this sense, you are reproducing similar conditions as you had in the Big Bang.
Yes.
And therefore, this study of the LHC is very useful for knowing what could potentially have happened in the Big Bang time. So in that way, you can say that you are learning about the time around the Big Bang, or much closer to the Big Bang, if there was one, than today. And therefore, it is a sort of Big Bang recreating machine.
Yes, exactly.
But it produces particles which are not so usually seen. And therefore, is now one of the particles that would be produced in this LHC contributed unusually much and strong contribution to the imaginary part of the action. Then it could be that you would make the dependence of the choice of the initial condition of the start of the universe depend very much on what goes on when you begin to play with LHC.
Yeah.
Much more than what goes on. It would be much more sensitive to that than what goes on today. Because it could be that some of these particles were more effective in contributing to the imaginary part of the action. You remember I said that in order that our theory should be not out of question, we have to speculate that what goes on in the early Big Bang should be or in the Big Bang time or era, so should be something more important for the imaginary part of action than most of the things going on today, because we like that the starting conditions should be mainly made to make a certain situation at Big Bang, and then it gets more and more complicated as time goes on.
Yeah, exactly. I see. And this is the thing here.
But now, we have a special speculation, which I think we have special arguments for, that especially the Higgs particle would contribute a lot to the imaginary part of the action.
Mm-hmm. And you have then here as well a few quotes from the article from the New York Times that I want to repeat and then discuss a little bit about this, because you said basically it must be our prediction that all Higgs producing machines shall have bad luck. One could even almost say that we have a model for God, and he rather hates Higgs particles and attempts to avoid them. Can you tell us about this a little bit?
Yes, I say that we have the speculation that when you have a Higgs particle present as a true particle, it doesn't live very long, but it lives for a little time, exists for a little time. Then such a Higgs particle is supposed to contribute a rather big number, which we think is positive, to the imaginary part of the action for that history in which this Higgs particle is occurring.
Mm.
So if a certain history has Higgs particles produced, then these Higgs particles contribute a positive and rather big number to the imaginary part of the action. So this means that the history in which you produce many Higgses will have all the rest equal a bigger number, a less negative imaginary part of the action, which means that a history with production of many Higgses has a smaller chance to be the one that would have been selected start conditions for than another one. So if you have a history in which a machine producing a lot of Higgses had good luck, then this history would have made its own chance for being selected as the one to be realized, namely the one having the minimal imaginary part of the action. It would make that chance very small.
So what you're saying basically is that we are currently not living in a universe where this has happened because we can't seem to get the LHC going. Is that what you're saying, if I simplify it?
Yeah, I'm saying that a universe in which the LHC goes well and produces a lot of Higgses is a universe that has, from our period, a contribution to the imaginary part of action, which is a positive big number. And therefore, that universe, that history, I should rather say, that potential history of the universe in which this happens is unlikely to be the winner of the game of having the smallest possible imaginary part of the action.
How about that? So, I mean, what does this say about, I mean, there's different theories out there even pointing to the fact that we might be living in a simulated reality, that we might be experiencing all of this in some kind of a quantum computer simulation or what have you. Would this confirm
or think that kind of things?
Yeah.
And in a way, of course, you can say that this God in quotation mark that looks at all solutions and uses his computer to find the one with the smallest value, that he is a bit of a simulator playing with the story, and then decides to use that story to decide which universe to start. But I don't know. I mean, maybe maybe these kind of stories about us being simulated by somebody else, and so that's another wild speculation.
Yes.
And maybe we should only have one wild speculation, namely our model in the game now, and not mix them up.
A bit too complex
but I
otherwise.
think there is actually a bit of similarity with this simulation, because it is almost as if we are selected by this God in quotation mark, and that he is a sort of great computer guy sitting and playing with us. But
would you?
So there is, maybe you can use it as a pedagogical game.
Yes. Now can we? How should I put this? Can we learn something in regards to our future with a model like this? Can we predict things in terms of future events, or are we still?
Well, in a way, I'm doing that.
Yeah.
Because me and Marcel Mia, who is the collaborator on this version of the model, we are in a way predicting the bad luck for these machines producing a lot of Higgses, and especially, of course, we are concerned with LHC, and therefore we are somehow predicting the future, because although the LHC has now started successfully a little bit before Christmas and will start again in the middle of February, then it is still running on a very, very low rate.
Yes.
Which means that the beam intensity is very low. This beam, which runs in the LHC, it is divided up in some bunches and a few centimeters, 5 centimeters long, and with something like 9 meters between. And they are running around 27 kilometers. So you can calculate how many 9 meters there are in 27 kilometers. So there are many bunches. And that is what is meant to be done when it really runs. But until now, I think you had only one bunch in it. So you were running with a much lower lower intensity than it shall do in the long run. And therefore, I think until now, no Higgses have been produced so far.
Yes.
And therefore, there was, strictly speaking, no reason for our God, in quotation mark, to kill it as far. So he has still time to do the job. Of course, and I should also mention that there is a smaller machine in Chicago, in FNAL, Fermilab, called the Tevatron.
Yes.
And although this Tevatron has not seen that it has produced any Higgses, then in very great likelihood it has already produced several thousands of Higgses.
Mm-hmm.
And it will take the LHC probably the rest of this year to reach a similar amount of Higgses being produced. And probably it will also not have seen them at that time. But this depends on the mass of the Higgs, which we don't know exactly, but only order of magnitude. But so if this amount of several thousand Higgses is not enough to sort of exclude that our history could be a good history, winning the game or being the minimal imaginary part of action history, even if you have about 5,000 Higgses produced, then maybe also the LHC would be allowed by the God, in quotation mark, to make similar amount. And therefore, in a way, he has the chance that he can still, it's still not urgent for him, perhaps, that he has to stop the machine after this year. But of course, it is statistics that it is a matter to do it what is most easy and least miraculous for him to do it. So he could perhaps have chosen to do it, and the longer he waits, the more embarrassing for our theory, which means the more likely that our model is wrong. But it is not really severe yet. Okay. What would be severe for our model would be if this God, in quotation mark, doesn't stop the LHC before it produces as many Higgses as this machine in Texas, the SSC, meaning the superconducting supercollider, would have produced. Because if it goes beyond that, we might still put parameters in our theory and say, okay, that's how it should. But then we would lose our best example of a bad luck for a machine producing a lot of Higgses. Because the best evidence for this kind of story, the only really weak support, there is no strong support, only this weak one and another weak one, that would be that this SSC machine in Texas, the superconducting supercollider, did not come to work ever because it was stopped by the Congress. The budget was candied by some milliards and so on of dollars. So it got bad luck in that sense. But if this bad luck was just an accident and not a bad luck due to our God in quotation mark, then we are losing the best evidence. So then I think our trustworthiness of our theory would be very low.
But there's still a possibility for something, a unknown variable, so to speak, to come into the picture here, where these things, where either the superconducting supercollider in Texas or the LHC stops in some way, or they're not, they won't achieve what they're trying to achieve there, and that would still then give credence to your theory or your model, and it will hold up, it will stand, right?
No, I mean, it gives a little bit of support of our model that this SSC had the bad luck.
Yeah.
This is supporting now, and it is also supporting that the LHC had the bad luck last year in September, because that prevented it so far.
Yes, and there was
from doing anything. So now there is still a chance that something more severe could happen.
Absolutely, there was something strange that happened in terms of. I think there was. I read an article about there was a bird. They speculated why the reason why it stopped, the breadcrumb or whatever.
I think that's a little bit exaggerated, but it is true that there was a bird that lost some baguette into some electricity components, and there was a breakdown of the current, and of course it also delayed the machine a little bit.
Yes.
But just a current fallout is, of course, I mean, the machine is, of course, made so that a current fallout will not be a catastrophe.
No, that's
so
true.
If this God, in quotation marks, should want to kill the machine, it is not enough with the bird losing a bit of baguette into the current and making a breakdown.
Absolutely. Holger, what I want to do right here is take a short little break and then continue talking more with you here in the next segment. I have so many more questions for you and points that I do want to discuss, but beyond that, just to round things up here for the first segment for us, do you have any website or something like that you can give out to our listeners if they want to follow your work more closely and some of your theories and so forth?
I'm afraid I haven't really made a website, but we have, what can we do? I mean, we can, I have some papers about this. We have some articles about it, which one can read.
Yes.
And I have, for instance,
sorry to cut you off here, but...
An article meant for a more popular purpose.
Yes.
And that is one can find it via Spires, and it is also published by Aarhus. It is published by Aarhus University Press in Danish. But you are Swedish, so you can read Aarhus University Press book, and it is in a book called Miracles.
Yes.
And this is a series of talks by various people talking about miracles. There is, of course, some theologists and a magician and myself.
There you go.
And I'm talking about a talk called Naturlovsmodel med mirakler. Natural law model with miracles. And this article I have translated into English, and it is on the Spires. One can get it in English. I think it should be possible somehow to get it via Google also.
Yes.
It is accessible on the net in principle.
Okay. Well, and what I will do then is basically I will do a search for this paper and link up the English version for our listeners. And you also have a personal web page through nbi.dk.
Yes, I have. Yes,
yes.
you can find a personal web page on NBI for me, and yes.
Okay.
So that is another way to get. And I should say perhaps that this project is, I consider it a part of a bigger project called Random Dynamics,
Yes.
which was also mentioned in New York Times.
Absolutely, and that's something I want to talk more with you about later
and
here
for that,
in the next segment.
we have a net page called Random Dynamics is Streaming, and you can get it by Googling on Random Dynamics.
Right.
And this is one that has been organized as web page with the help of a Norwegian Swedish physicist called Astrid Klippe.
Mm-hmm.
So you can log in on this Random Dynamics, and there you can find a lot of pages about this project of Random Dynamics. Most of them are not extremely popular, but but this is about this project, and I hope that also there should be perhaps access to this article about miracles from this book by Aarhus University.